Good morning children. Welcome to GCC Education YouTube class. Today we are going to start the next chapter in 12th Physics, Current Electricity. First lesson electrostatics we saw about the charges at rest. In this lesson Current Electricity we are going to see about the charges in motion. For this we are going to concentrate only on conductors because only conductors have charges, that is free moving electrons. Okay. We all know we use only copper wires for electrical conduction because copper is a good conductor. Let us just see how copper can ensure the free current supply. Copper, the electronic configuration we all know, it is 2, 8, 18 and 1. How this will be arranged in the atom? The structure of the atom you all know. Center you have the nucleus and around the nucleus you have specified orbits in which the electrons move around the nucleus. The first orbit has 2 electrons, the second orbit 8 electrons. In third orbit copper has 18 electrons and in the fourth orbit it will have 1 electron, which is incompletely filled orbit, and this electron will be very loosely packed with the nucleus. Even at room temperature this electron will come out of the atom and it will be moving freely in the substance. Here we have drawn only a single copper atom, but if we take a wire it will have millions of copper atoms. Each copper atom will contribute a free electron. So let us assume this is a copper. This is the whole copper wire. I have drawn it in a magnified manner. In this copper wire you have millions of copper atoms. If each copper atom gives rise to one free electron, you will have millions of free electrons in this copper atom, and even at room temperature these free electrons, it will come out of the copper atom and it will be moving freely in the substance. So these free electrons will be under random motion. So it will be under random motion. So, but this free electrons which is having random motion cannot constitute any current. Only the electrons moving in a particular direction will constitute an electric current. So these free electrons, even though it undergoes random motion, this random motion, each and every electron will be moving in different direction, and the number of electrons moving in a particular direction will be equal to the same number of electrons moving in the opposite direction, and so there won't be any net transfer of electrons. For example, I will just show you, these are the free electrons in the copper substance. These free electrons, each free electron will be moving in random directions, and there won't be any net transfer of electrons. Even though the electrons are moving, there won't be any net transfer of electrons. How can we understand this? Supposing if we have n number of electrons moving in this direction towards the right, then same n number of electrons will be moving in the opposite direction towards the left. Supposing if I consider there are n number of electrons moving in this direction, then there will be n number of electrons moving in the opposite direction. So naturally the number of electrons moving in any direction will be equal to the number of electrons moving in the opposite direction, so that there won't be any net transfer of electrons. So since there is no net transfer of electrons, there won't be any electric current. So random motion of free electrons inside the substance will not constitute any electric current. So how to get the electric current? You have to make the free electrons move in a particular direction by applying an external electric field, like external potential difference. That means you have to connect a battery. Battery will have two terminals, one negative terminal, another one is positive terminal. Negative terminal is connected in this left side of the substance, and positive terminal is connected in this end. Now what will happen? Once you connect the external battery, external potential difference, all the free electrons will get accelerated towards the positive end of the battery. So without the external potential difference, there won't be any electric current. With the application of external potential difference, electrons will be drifted towards the positive end of the battery. So there is a net transfer of electrons towards the positive end, towards in one direction, that is towards the positive terminal of the battery, and hence there is an electric current. So now we all understood how the electric current is produced by the motion of free electrons in the case in conductors in particular direction by the application of external potential difference. Now let us define this electric current. Electric current, as we all understood now, the electric current is only because of the flow of charges, that is charges means the electrons. So the electric current can be defined as the rate of flow of electric charges, rate of flow of charges through a given area of cross section. If you consider this is the area of cross section, the number of electrons crossing this area of cross section, normal to this area of cross section, A is called as it's defined as the electric current. So rate of flow of charges through a given area of cross section is defined as the electric current. It is denoted by the letter I. I is equal to Q by T, where Q is the amount of charge that is flowing through the area of cross section A for a time T. So this is the general expression which we use for the electric current. But actually the amount of electric current, that is the amount of charges that is flowing through an area A for a particular interval of time, will not always be the same. So for regular intervals, even for regular intervals of time, the amount of charges flowing through a given area of cross section will not be the same. So in that case we have to define the average current. So the expression for denoting the average current, I average, is equal to, you have to use the symbol del Q by del T, where del Q is the charge that is flowing through the area of cross section A for a time del T. Del T is a very small interval of time. Now even defining the electric current very precisely, we can define the instantaneous current. At any particular instant, what is the electric current? That is, when the time period is very short, that is del T tends to 0, what will be the current? So I instantaneous is equal to del Q by del T is the previous equation which we wrote. So here for writing the instantaneous current, you have to take the very short interval of time period, that is limit del T tends to 0. This we all know how to write this. Del Q by del T, limit del T tends to 0 is written as dQ by dt. So the expression for electric current I is dQ by dt, where dQ is the charge and dt is the time, and the unit of charge you all know coulomb, and the unit of time is second. So unit of current coulomb by second, but SI unit of current is normally written in ampere. 1 coulomb by 1 second is nothing but 1 ampere. Ampere, the symbol is capital A. Now we are going to define the unit of current, that is ampere. How will you define ampere? Current will be 1 ampere when 1 coulomb of charge flows through an area of cross section A in 1 second. So this is how we define the unit of current, that is ampere. Current is 1 ampere when 1 coulomb of charge crosses normal to the cross section area A in 1 second. So current is a scalar quantity. Then the current here we are mentioning is only the conventional current. What is this conventional current? Conventional current is taken in the direction of the path of the unit positive test charge. That is, now supposing if we have a unit positive test charge, then unit positive charge will move towards the negative terminal. But here the current is due to the flow of electrons, which is from negative terminal to positive terminal. Electrons will flow from towards the positive terminal, that is in this way, that is from lower potential to higher potential. This is negative terminal, which is the lower potential. This is positive terminal, which is the higher potential. So this end will be at a lower potential than this end, which is at a higher potential. Now conventional current is nothing but the path taken by a unit positive test charge. Unit positive test charge will always move in the in this direction, that is from higher potential to lower potential. So always we must remember the direction of conventional current is always in the direction opposite to the direction of the flow of electrons. So conventional current always flows from higher potential to lower potential, but electrons will always flow from lower potential to higher potential. Now, based on this formula which we learned today, current is nothing but charge by time. We are going to see a first example problem, example 2.1. This problem is a very, very simple problem which you may get in 1 mark or in 2 marks. Compute the current in the wire if a charge of 120 coulomb is flowing through a copper wire in 1 minute. So, the given quantities we have to write first. They have given the charge Q as 120 coulomb and the time T as 1 minute. Minute, if they give time in minute, you have to convert it to the SI unit, that is seconds. 1 minute is equal to 60 seconds. So, they have asked to compute the current. So, current is I is nothing but charge by time, Q by T. Charge is 120 by time is 60. So, here 0, 0 will get cancelled and in 6 table you will get 2 ampere. So, the current is 2 ampere. Children, don't forget to put the unit. Unit will carry mark, right? So, current is equal to, whenever you do problems in physics, at the end, once you compute the answer, don't forget to put the unit of the physical quantity which you are computing. So, I is equal to 2 ampere. Let's move on to the next topic, children. Drift velocity. Already we have seen, when you apply an external potential difference to a conductor, see, this end is connected to the negative terminal of the battery and this end is connected to the positive terminal of the battery. As we all know, the conductor possesses lot of free electrons which are in random motion. Once we connect the external potential difference, these electrons will be drifted towards the positive terminal of the battery. So, while doing so, each and every electron will be accelerated towards the positive end of the battery, and when they move from this left end to the right end, they will collide with the positive ions present in the element, in the conductor. Actually, previously when we started the lesson, I told you, each and every atom in the conductor, it will lose its free electron. Once the atom loses a free electron, the atom will become a positive ion. So, inside the conductor, you will have both the free electrons and the positive ion. The positive ion will also, the atom which will become into a positive ion because it has lost the electron. So, when the electron is accelerated towards the positive end of the battery due to the application of an external potential difference, let us, for example, let us take this electron moving towards the positive terminal of the battery. When it gets accelerated in this direction, what happens? It will collide with the positive ion. Due to collision, it changes its path and travels in this direction. Again, it may collide with some other positive ion. Again, it may change its direction. Again, collides with another positive ion, changes its direction. Again, collides with the positive ion, changes its direction. So, once it moves from this end to this end, it doesn't travel in a straight line, but it travels in a zigzag manner due to successive collisions with the positive ion. So, this velocity, the velocity will not be the same at all times from this end to this end. So, we can only speak about the average velocity. So, this velocity, the electrons are being dragged, so drifted from one end of the substrate wire to the other end. That is why we call this velocity as drift velocity. Drift velocity, it is the velocity with which the electrons move in a zigzag manner, is called drift velocity. So, you have understood clearly the electron cannot travel in a straight line due to the collision with the positive ions. It travels in a zigzag manner. This is called as the velocity. This velocity with which the electrons travel in a zigzag manner is called as drift velocity. So, let us define this drift velocity. So, I told you, due to successive collisions, we have to take only the average velocity. So, average velocity occurred by the free electrons when subjected to the external electric field. This is the external electric field, and the direction of the electric field you all know, away from the positive, like this. So, this is the direction of the electric field, external electric field, and due to this, the average velocity occurred by the free electrons when subjected to electric field, external electric field, is called as drift velocity. It is denoted by the letter V suffix D. So, velocity with the letter V, and since it is a drift velocity, you use a suffix small d. Now, we are going to define the next term, mean free time tau. Now listen carefully. We took only this electron for example. It undergoes successive collisions and travels in a zigzag manner. Let us just say for example, at the time T1 it collides with this positive ion, T2 the next collision occurs, T3 the next collision occurs, T4, T5, and different times these collisions occur and this electron travels from this end to this end. So the average time between successive collisions is called as mean free time tau. Mean free time is defined as the average time between successive collisions. Successive collisions na adutadutha collision. So T1 the first collision occurs at the time T1 and the second collision occurs at the time T2. So what is the time difference between these two collisions, these two successive collisions? It is T2 minus T1. Similarly, these two are successive collisions. So the time difference is T3 minus T2. Similarly, T4 minus T3, T5 minus T4, T6 minus T5. Similarly, you can find the time difference between successive collisions and average of all this time will give the mean free time. So mean free time is not tau, it is denoted by the letter tau. You have to write a symbol, you have to write like this, you have already learnt in 11th standard. So mean free time is nothing but the average, it is the average time between successive collisions. Now we are going to find the expression for the drift velocity and then we are going to define the mobility, term mobility. For deriving the expression for drift velocity, let us take the acceleration that is occurred by the electron. Since we are applying external potential difference, all the electrons will be accelerated towards the positive end of the battery. So let us write the expression for the acceleration A vector occurred by the electron. Newton's second law, we have to use only Newton's second law, F is equal to mA, from which A is equal to F by N, and we all know the relation between F and E which we have learnt in the first lesson. F is equal to EQ is the relation between force and electric field E. So A is equal to F by M. In the place of F you have to substitute EQ. Here Q is the charge. Here which is the charge? The electron. What is the charge of the electron? Small e. So instead of Q we can use small e, and since the electron possesses negative charge you have to use one minus sign also. So the formula for F will be minus EE, capital E, small e. So acceleration is force by mass, and for force you substitute minus EE by M. Now we are going to find the drift velocity. Normally how will you define velocity? Velocity is nothing but rate of change of displacement. And how will you define acceleration? Rate of change of velocity. That is acceleration A is equal to V by T. So what is velocity? Acceleration into time. So velocity is nothing but acceleration into time. So velocity here in this case we are speaking about drift velocity. So for velocity you write drift velocity Vd, acceleration is A vector, into time is nothing but mean free time tau. So Vd is equal to A into tau. So Vd is equal to, in the place of A you substitute minus EE by M. So substituting you will get Vd is equal to minus EE by M into tau. So here all these are constant except for the electric field E which is applied externally, whose value we can change. So this you take it outside and all these put together you get Vd is equal to minus E tau by M into E vector. Now leaving this negative sign, take only this quantity E tau by M. It is defined as the mobility of the electron. Mobility, it is denoted by the letter mu. Mu is equal to E tau by M, the mobility of the electron. Now substitute in this drift velocity expression E tau by M, take it as mobility. So you will have Vd vector is equal to minus mu E vector. So we are going to define the mobility. So keeping mobility mu here, take this electric field to this side, it will come to the denominator. Mu is equal to Vd vector by E vector. You can just remove the negative sign because we are going to consider only the magnitude for defining the mobility. Mu is equal to Vd vector by E vector, magnitude of Vd vector by magnitude of E vector. So from this expression you can very well define the mobility. Mobility is equal to the drift velocity when the electric field is unity. So magnitude of drift velocity occurred by the electron. This is the mobility is nothing but magnitude of the drift velocity occurred by the electron per unit electric field. So this is how we define the mobility. So mu is equal to, let us write the unit, derive the unit for mobility using the same formula. Mu is equal to Vd by E. Velocity, the unit is meter per second. Electric field, we know the unit volt per meter. So m by s into this, when it comes to the numerator, you will have it as, you just put the reciprocal m by v. So unit of the mobility mu is meter square by volt second. This you have to remember, children, very important 1 mark question. Unit of mobility is meter squared by volt second. Now based on this expression, for we can one problem is given. Example 2.2, if an electric field of magnitude 570 Newton Coulomb per minus 1 is applied in a copper wire, find the acceleration experienced by the electron. So they have given only the electric field, E is equal to 570 Newton Coulomb power minus 1. What they have asked us to find? Acceleration experienced by the electron. So we have already written the expression for acceleration. Acceleration is E by m. So here we are going to use this formula. We are going to find only the magnitude, because this negative sign only represents the charge carried by the electron is negative. So you can just omit the negative sign, use only the formula. Acceleration is equal to E by m. Here they have given the electric field E. Now the charge of the electron and the mass of the electron, you have to remember, children, charge of the electron, charge carried by one electron is 1.6 into 10 power minus 19 Coulomb, and mass of the electron is 9.11 into 10 power minus 31 kilogram. Substituting all these values, see this 10 power minus 31, if you bring it to the numerator, minus 19 plus 31, how much? 12, 10 power 12. Now this 570 into 1.6 is 912. So this since in the new denominator I have 9.11, I will make this also into 9.12. So into 10 power 2 means you will get 10 power 2, 10 power 12. Now 9.12 by 9.11, it is around, it is nearly equal to 1, that is 1.001 into 10 power 14. Unit of acceleration is ms power minus 2. So very easy, children. Given only the electric field, you can find for electron, since it's an electron, you know the charge of the electron, you know the mass of the electron, you can easily find the acceleration of the electron. Very simple problem, this you may learn. We will pass on to the next topic, children, which is microscopic model of the current. So the same consideration we are going to take. The conductor, one end of the conductor is connected to the negative terminal of the battery, other end is connected to the positive terminal of the battery. So external electric field is applied, which acts in this direction from right to left. Now we are going to derive the expression for the current and then the current density, and the expression for the current density is nothing but the microscopic model of the current. For that, let us just consider, we all know this substance has number of free electrons, and once the external electric field is connected to the two terminals of the substance, what happens? The electrons, the free electrons are drifted towards the positive end of the battery. Now for our derivation, we are going to consider a very small element of length dx of this conductor, that is this area of cross section, this is another area of cross section. Consider only this part, this element of the substance which is of length dx, the very small length dx. Now we all know the charges are crossing this area like this from left to right, and they cross with the drift velocity Vd, and they cross this element in a time dt, the time is dt. So velocity, we all know velocity is equal to distance by time. So distance is equal to velocity into time. So this distance dx is also equal to the velocity into time. Velocity is nothing but the drift velocity and the time is dt. So Vd into dt. Now A is the area of cross section. Now let us consider the number of, we are going to find the volume of this element. So let us now first define the number of electrons present per unit volume. So number of electrons present per unit volume is taken, we are going to take it as small n. So first let us find the volume of this element. How will you find the volume of this element? Naturally area into the distance, A into dx, and distance is nothing but velocity into time dt. So volume of the element is equal to area into distance, which is velocity into time dt, A Vd into T. Now the number of electrons present per unit volume is small n. So what will be the number of electrons present in this whole volume of the element? You have to multiply this term by n. So total electrons in the element is, multiply this term by n, small n, you will have NaVd into dt. Now we want to find the current. For current, what is the formula? dq by dt. What is dq? The total charge. So total, we have to find the total charge present in the element, in this element. Let us say the total charge present in the element as dq. How will you find the total charge? The number of electrons we have found, the number of electrons in the element we have found. So what is the charge carried by one electron? It is small e. So what will be the total charge of this number of electrons? You have to multiply this by E. So NaVd into dt into charge of one electron, which is small e. So now we can easily find the current. Current I is equal to dq by dt. For dq you substitute Ne, you multiply inside NeaVd into dt divided by dt. So the dt in the numerator, dt in the denominator will get cancelled. You will get for I as NaeVd. This is the expression for the current. I is equal to NaeVd. Now we are going to define the next quantity, which is the current density. Density means what? Per unit area. That is, the current per unit area will give us the density, the current density. So current density is nothing, denoted by the letter J. It's a vector quantity. J vector is equal to current per unit area, that is I by A. Unit of current is ampere, unit of area is meter square. So ampere meter power minus 2 is the unit of current density J. So current density J is equal to I by A. You can substitute what I we found previously, NaeVd here. So J vector is equal to NaeVd by A, because J is equal to I by A. So here again numerator la irukra A, denominator la irukra, it will get cancelled. You will have NeVd, and already we have found the expression for drift velocity as minus E tau by m into E vector. So substitute this Vd in this expression for current density. J is equal to Ne into Vd. Ne into Vd you substitute minus E tau by m into E vector. So here you have 2E, E into E you will get E square, minus you take it common outside, minus N E square tau by m into E vector. Now again what we did for mobility, keeping the variable E outside, all other quantities are constants. So this constant is nothing but the conductivity of the substance, sigma, denoted by the letter sigma. Sigma is equal to Ne square tau by m. So sigma is called as the conductivity. So J vector is equal to minus sigma E vector. This is the very important expression. This is the microscopic model of the current. Now this sigma is the conductivity. As we all know, the reciprocal of the conductivity is resistivity. So rho, resistivity is denoted by the letter rho. Rho is equal to reciprocal of conductivity, that is 1 by sigma. Already we know the expression for sigma. Rho is just the reciprocal of sigma. So just inverse and write m by n E square tau. So we have arrived at the microscopic model of the current. We have defined what is sigma, conductivity, what is rho, resistivity. With this we wind up this session, children. Please go through your book. What are the portions taught today? Please go through your book and learn. Thank you, children.